My name is Michał Stęchły, and this is Noisy Intermediate Scale Podcast, a podcast where we'll have in-depth discussions about quantum computing industry, community, and research. Hello. Today I'm talking with Nicolas Sawaya, a research scientist at Intel working on quantum algorithms for scientific applications. We talked about his work at Intel, climate change and how quantum computing could help, and his research about vibrational problems and various problem encodings for quantum computers. You can find links to most of the papers we talked about in the notes of this episode. I hope you'll enjoy listening to this conversation. Hello, today I'm talking with Nicolas Sawaya. Nico is a research scientist at Intel, where he works on developing quantum algorithms. He finished his PhD in chemical chemistry at Harvard in Alan Asparuh Group. His main research interests are near-term quantum algorithms for quantum chemistry and material science. Welcome to the show, Nico.
Thank you. Thanks for having me. I'm excited.
Great. The first question is, what are you currently working on, and why do you think this is important?
Yeah, so I work primarily on algorithms development. I do a few different things inside Intel Labs, but mainly I've been looking for and studying new application areas for chemistry and material science. The field of quantum computation has been around just for a couple of decades, and for that whole time, the understanding has been that you'd be able to use a quantum computer to simulate real substances in the real world. But there's quite a few areas that have been neglected simply because, partly because researchers haven't gotten around to it yet. And one of those areas is simulating vibrational degrees of freedom. So there's all sorts of problems where, it's difficult to determine the properties of a molecule or a material that arise from the vibrational behavior of those materials. So some examples of that are like spectroscopy. This is a common method in chemistry, in physical chemistry, to either probe what's happening in whatever experiment you're doing, or simply to be able to identify what molecule you're looking at. So one example of this is astrochemistry, which is really cool. There's this telescope array in the desert in the mountains in Chile, where they have these. It's called the ALMA telescope array. Yeah. They essentially point these telescopes to the sky, right, at other planets other than Earth, and they can absorb photons, right? They detect photons coming in, and from those photons you can determine which organic molecules or other types of molecules might be on those planets, right? And so that's one application. But there's all sorts of other properties that arise from vibrational behavior, and for a lot of those problems, it's essentially too difficult to simulate those problems on a classical computer. So that's one big area that I've been working on, and there's some related areas as well.
Oh, cool. We'll definitely get back to this later, but actually, could you tell us something more about your work at Intel?
Yeah, so I do algorithms development, but so I can't talk too much about the things I do that aren't public and published. But there's a hardware team. Mm-hmm. Of course, we work on a type of qubit called a quantum dot, and so I play some support roles sometimes in that effort. I can't talk too much about it, but it's the sorts of things that you would imagine from someone who designs algorithms and who writes simulation software, right?
Yeah, sure.
So, preparing small-scale algorithms, trying to get them to fit onto whatever hardware we happen to have, that's a big topic that you're familiar with too, I'm sure.
Oh, yeah.
And different types of simulation tools that might be helpful to the people actually trying to build the real hardware. So there's a mix of that and then kind of the real hardcore academic-style algorithms development that I do.
Sure thing. And actually, when it comes to the hardware you have at Intel, well, Intel is not one of the most, public company in the quantum computing space. Doesn't do a lot of marketing or whatever. So actually, I think most people don't really know what's the specific hardware you are working on there. So if you could tell us anything about it, that would be great.
Yeah, so you're right. We do keep tight lips, kind of, but we do focus primarily on a technology that most of the other big competitors don't focus on. So a lot of the progress in the field more broadly has been in superconducting qubits.
Yeah.
As you know, Intel focuses primarily on quantum dot qubits, and there's a few important differences, and there's pros and cons for each technology, but I can kind of give you a summary of the reason that Intel focuses on quantum dots. One of them is that these are silicon-based, devices, and they have features similar in size to the features that Intel has been used to manufacturing for decades, right? So Intel has massive manufacturing capabilities, very sophisticated methods for making the types of chips that are inside your computer or your phone or whatever. And the idea is that we can use all of that really sophisticated, very secret technology to be able to produce better spin qubits. So that's one reason. But just more generally, quantum dots are much smaller. And because of that, it seems likely that they're going to be easier to scale up, right? So once you've gotten to a few hundred qubits, it's likely that it'll be easier to scale up quantum dots than it will be to scale up superconducting qubits. So clearly it was more straightforward to get to something like 100 qubits for the superconducting qubits. But that next step, you have quite a few problems with scalability that you don't seem to have with quantum dots. A couple other things, they can run at slightly higher temperatures. So superconducting qubits need to be at a few millikelvin, or I guess a few tens of millikelvin, right? Just above absolute zero. But quantum dots, maybe you can get up to a Kelvin or two. These are still really low temperatures, right? But that's another advantage, and it means... Yeah, go ahead.
No, it makes a huge difference, I think, in the kind of cooling down process. This last mile is really hard to get in superconducting. So even it's but this actually you can think about 1 Kelvin versus 10 millikelvin, but this is actually 2 orders of magnitude. So that's a lot.
Exactly. Yeah, and as you add more hardware, more controls for the qubits and more qubits, then that's going to heat up, of course. Yeah. But within Intel, the hardware effort is led by Jim Clark. So if anyone's interested, I would encourage people to Google his name, because he's done some public interviews where you can get a lot more details than what I have access to. And then on top of the actual hardware, Intel really focuses on what we call a full systems approach. So we spend, and this is under Ann Matsuura's group up in Oregon also. And so her group focuses on essentially everything above the control hardware, right? So making sure that this kind of ecosystem of compilers and problem preparation and analysis of new algorithms and all this stuff is really ready to go once we're scaled up to more qubits.
Sure. And do you know if there are any other groups working on quantum dots qubits, or are you the only one?
There are a few. Yeah, there's some academic groups and also a few private companies as well. Yeah, but the very big kind of established. I'll just leave it at that.
Okay. Yeah. Sure.
Yeah.
So one of the things I'm curious about is how involved you are in development of the hardware. So how tight is the coupling? How much your work as a researcher who develops algorithm influences the way the hardware is actually designed? Yeah.
So I'm not the only one in the company that develops algorithms, but There is, as you can imagine, a strong connection between the people who are algorithms experts and the people trying to run hardware. So you might be more familiar with this than I am, but in traditional computing, there's a concept of hardware co-design, and that's the concept where you basically you try to design the algorithms that the hardware is going to be used for and the hardware at the same time. Right? It's kind of co-design. Yes. So if you're designing some kind of new high-performance chip for deep learning or something, you make sure that you have all the workloads you would use in machine learning kind of analyzed, and you design the hardware in a way that's based on performing well in those algorithm areas. As far as I understand, I'm not an expert in this area, but as far as I understand, traditionally classical computing was able to chug along largely simply by improving clock speeds and improving manufacturing processes. Moore's law just essentially guaranteed that even if you didn't analyze algorithms too much, things would move along very quickly. But in the past couple of decades, hardware co-design has become more popular. And so Ann Matsuura, the leader up in Oregon who I mentioned, is really pushing this approach of trying to do this co-design, making sure that we're kind of doing the algorithms and the software in tandem. And I play a small role in that. There's other people who play a bigger role. And then, as I mentioned earlier, I've been involved in writing some large-scale simulation software. And so that tends to be useful for analyzing hardware parameters, and to some extent knowing how to have a efficient layout of the qubits. How are you going to arrange them on the silicon, right?
Yes.
Those types of questions I've played a small role in looking at, right?
Okay, so now let's get to another topic that I wanted to talk with you about, which is climate change. I know that climate change is something that concerns you a lot, and we are both involved in the Q4 Climate Initiative with also a couple of other people. The goal of the initiative is to find how quantum computing and quantum technologies in general can help with the climate change. It's still a work in progress. We don't have anything definite to show to the world, but I'm curious, what did you learn in the last couple of months when we've been working on this? Are there any insights that are interesting to share?
Yeah, so maybe I could describe the initiative a little bit.
Yeah,
so
sure.
So I joined after you, but it's an initiative of a few people, and the idea is to study how quantum technology can be useful for climate change, essentially. So however interpreted, right? And so it's kind of split up into a few groups. I guess you're kind of, with Stuart Hadfield, you're doing the quantum combinatorics for those types of algorithms that might be helpful for clean energy. I'm on the team that looks at quantum simulation, so the types of simulations that would, help you develop new solar panels, new batteries, new technologies, that kind of thing. And then I think there's only 4, right? And then there's a group that looks at the energy consumption of quantum computing.
Yes.
And then Tracy does the quantum sensors. So,
Exactly.
In the simulation area, I'm essentially regurgitating the things I know onto the page for some of these reports that we're writing up. But I've learned a lot about this sensing technology. That was really interesting for me to learn about how much quantum technology and quantum sensors can make a difference, right? They can be much more sensitive. They can be cheaper in principle, that sort of thing.
Yeah.
I think that's the main area where I didn't know anything before, but I've learned quite a bit.
Sure. It's also not quantum computing. It's like not connected to quantum computing except for the fact that it's basically quantum mechanical thing. So I think it's much more mature technology, and there are already sensors like this in the market. So that's also kind of exciting because we don't have to wait 20 or 30 years for fault-tolerant quantum sensors. You can use them today. It's just a matter of designing better ones. Yeah.
Right. Can I ask you what the main things you've learned so far?
Sure. So for me, one thing is I realized how far we are and how long the road is before we'll be able to actually tackle some of the big problems. There might be specific applications that might work out earlier, but in general, I didn't appreciate how complicated this problem is. Like the problem of making quantum computers work, but also climate change problems, in the sense that even if we manage to, tomorrow have a way to solve, for example, combinatorial problems like traveling salesman faster, better, and basically instantaneously, it doesn't mean that it will actually help with climate change right away, because there are so many other things like policy or like second or third order effects that is just like all very complicated. And working on this helped me think more carefully about these problems and just realize that quantum computing will be just one small part of the solution, but definitely it won't solve all the issues. Not that I thought before that would be the case, but I really started to appreciate this fact much more after thinking about it more.
Yeah, and I really appreciate that the whole team, I think, has the same attitude that you just expressed. We're being really cautious not to oversell the potential. It's impossible to predict, really.
That's true.
And I totally agree with what you just said about policy. If there's no policies to phase out coal power, for example, it doesn't really matter if quantum computation can speed up other technologies. Well, it might still matter, but it's almost canceled out by continuing to burn coal and that sort of thing.
Yeah, that's true. And also regarding the kind of position we all have, like, it's kind of a little bit contradictory, I think, because on one hand we are all very cautious about it, but at the other hand, like, we're actually very hopeful that this will make a difference. We just kind of don't know it yet, and just trying to figure it out. So it's like an exciting place to be in the history of quantum computing, I guess.
Yeah, I agree, and it's worth exploring, regardless of what we end up, predicting or finding. So
yeah, like, negative result is also a result, right? Like, sometimes even scientifically maybe more important than the positive one. And
absolutely.
I'm curious, like, what are the time frames that you think about when it comes to quantum computing and climate science and climate change? What do you think, where quantum computers will start having some, not proof of concept, one plant somewhere impact, but rather actually something on scale and something that might actually make some real difference?
Yeah, so that's pretty hard to predict, as you suggested. But first of all, I presume that quantum computation is going to progress pretty steadily, but it's really hard to predict at what rate it progresses. So I think we'll keep seeing steady improvements in hardware every single year, probably is reasonable to guess. But if we don't see within 15 years a robust enough quantum computer to simulate even simple chemical problems, then I'm more skeptical that it'll make a near-term difference in climate change. And that's kind of the metric, Mm-hmm. There could be some major breakthroughs. There's lots of different technologies being studied, of course, right? And so it could be the case that you have millions of qubits within 10 years. I kind of doubt it. But I think that the first problems that would make the biggest difference, I think, would be small chemical problems. So it could be that you could get a decent amount of error correction, maybe, and enough qubits to be able to simulate like a simple catalysis problem. This is a really popular topic, how you would simulate catalysis. Maybe you'd be able to find a chemical problem that's not electronic structure, right? We kind of alluded to this earlier, that might be slightly useful. But I think until you have a really full-fledged quantum computer that might not come online for 20 or 30 years, maybe less, maybe longer, it'll be fun and interesting to try to kind of hunt out those edge cases where it might barely be useful.
Sure.
Right.
But basically, the time frame is probably not sooner than like 15 years. Maybe if we are lucky, but I guess that's...
Right. And I think the papers that we're writing, they're not public yet, right? But the simulation team in Q for Climate wrote something like, we essentially make this clear that we're not extremely optimistic that we're going to have, millions of qubits in 10 years in time to solve the climate crisis. But a lot of the paper is kind of what we would do if we had enough of a quantum computer to solve these problems.
Sure.
Yeah, I'm not extremely optimistic about the timeline.
Mm-hmm. And another thing, because like my understanding of chemical physics and chemistry is limited, but I'm curious whether if we find an edge case, like, if we have a quantum chip and we design it in a very specific way to be able to run very specific ansatz on that, right? So basically design hardware for the purpose of, this particular algorithm. And then we are able to, estimate the ground state energy of that particular molecule better than the current methods. Is this a way to actually get some meaningful results earlier? Because if we can predict properties of a certain molecule better, then we can feed it into like the whole existing kind of simulation pipeline that just uses classical simulation as like this first step. And then maybe we'll be able to actually get some meaningful improvement in the quality of the catalysts used in the industry, or maybe some material used for solar panels or whatever else. Like I have no idea. But do you think this path is feasible? If we're lucky, like we can get something like this earlier than this 15 years full tolerant quantum computer with a lot of qubits?
Yeah, I think you touched on two really important points. The first one, you suggested that maybe you tailor the hardware very specifically for specific problems, and maybe that would help design an ansatz that's very good for a particular type of chemical problem, for example. Yeah, I think that definitely needs to be explored. Again, impossible to predict, really.
Yeah.
But that if it happens, that it seems likely that would be the type of strategy that you would use. And then the other thing you suggest is that there might be some, slight improvement that comes from quantum computers. Maybe you can slightly improve the computational prediction capabilities that you have, and maybe that will, maybe increase the rate of true positive candidates for materials by 10% or something. Mm-hmm. Just to throw a number out there. Yeah. That's very possible, I think. I think maybe we're going to talk about the more general topic of computational materials later, but at the moment, the way computational materials discovery works and computational chemical discovery works is you do these massive screenings on supercomputers. Right? Yes. There's all sorts of research groups that do this. Spiro Guzik at Toronto, Christine Persson at Berkeley, Chris Wolverton at Northwestern. And it's kind of understood that these are approximations. And so you kind of maybe simulate 1 million molecules, maybe you rank them, you cut away the bottom ones, you don't want to waste time simulating those in the laboratory, and then you maybe simulate like the 100 best candidates that you got from the computation, and maybe only 3 of those actually work, right? Mm-hmm. And so it could be that you can improve those statistics, right? Maybe with a near-term quantum computer. Again, I don't want to say that you can. I'm pretty skeptical. We have to be honest about this, but there's a chance, I think.
And do you think, because I have absolutely no idea how chemical industry works, is it possible to just take those slightly improved numbers that we got from quantum computers, just like feed them into the computational pipeline, see whether they work? If they works, well, actually use that results on production much faster than the kind of regular like production cycle, which might take years, right? Do you think that's possible, or actually the way it's usually done, it will probably anyway? If we get good numbers, today we'll have to wait 3 years to actually see the impact they're making.
Oh, I see. I don't know enough, I guess, about the manufacturing process, but I'm trying to think if I have any examples of... It does seem like it's... So, I guess what you're kind of describing is first, in this pipeline, roughly speaking, first you do the computation, and then you feed those results to decide which material you're going to actually synthesize in the laboratory. Yeah. And then maybe you have another step of like really doing a lot of intense further analysis of that material, maybe how stable it is over time, stuff like that. And then building up the manufacturing process is extremely difficult also, right? Then you get a bunch of manufacturing engineers and do all that. Maybe this is what you were saying, but I would kind of agree that we're really only talking about that first step of determining what the good candidates would be. Yeah. And it's hard to see how the rest of those steps would be improved. Okay. Is that what you were alluding to? Or?
Yeah. This is just like same. I have very little idea of like how the rest of the process really looks like, and like in practice, how long it will take for this to propagate through to the end user, like to people who are actually building something with these materials.
Yeah. Actually, that would be something interesting to think about for the Q for Climate papers.
That's true. The problem is that
those steps.
That there are so many rabbit holes. It's just like impossible to cover all the topics. So just the problem of resource estimation, I think it's something that, I don't know, maybe it's like sometimes neglected in papers. So one of the projects we did at Zapata, like people were running some VQE simulations, but then when they actually did the math to check how many measurements do they really need to do in order to get to certain chemical accuracy, it turned out that, well, it would take like, I don't remember the numbers, like 1 year of running the chip like all the time. So it's not very practical. So even though like the algorithm looks okay, when you actually start making some assumptions more realistic, then suddenly some numbers can explode.
I'm aware of that paper. That was November last year that came out on the archive. So. That's the last author is our mutual friend Jonathan Romero, I think.
Yes, that's true.
Yeah. So one thing, that's really important, really honest paper that everyone should pay attention to. The one thing I'd say, this is pointed out by Krista Svore of Microsoft in talks that I've seen her give, which is that, in classical computing, it seems to be the case, or at least so I'm told, that algorithm development or algorithm speedups happened more quickly than hardware speedups did. Right? And so hopefully these types of problems that are brought up in that paper can be solved, just through algorithm improvements.
Yeah. And I think there was, I don't remember exactly, but I think there were two actual reviews from Google. In one, I think they analyzed the overhead of error correction, and the other, that was something different, when they showed actually how just improving the methods we are using is lowering the number of required resources, whether that was qubits or gates, I don't remember, but by order of magnitudes in a couple of years. So that
right.
One of the things that makes me hopeful that it might not be as bad.
Yeah, I see those papers as a call to arms for theorists and algorithms people, not necessarily as a pessimistic message to hardware people. It's,
definitely.
Exciting.
Definitely. Going back to climate change a little bit, I wanted to ask you also, what are some misconceptions that you see, or that the claims that people are doing, are making about things where quantum computing could be used for helping with, climate change or other big issues that you think are not very realistic, and be it due to the fundamental reasons or due to this kind of resource estimates not really making it possible anytime soon. Is there anything like this that you noticed?
Sure. So first I should say, some of these are my personal opinions, right?
Sure.
Views that are my own, all that stuff. So I think so there's been quite a few, somehow FEMOCO, this iron complex that's used by some organisms to fix nitrogen. Somehow that's kind of become the standard benchmark to study when you're trying to do research counts. A lot of your listeners should be aware of that. I think everyone working on those projects would acknowledge that it probably won't happen in 10 years, right? And you do occasionally hear people outside the field kind of misunderstand how difficult it's going to be to simulate chemistry. So that's just kind of a general comment. I guess we kind of touched on that already.
Yeah.
And then there's other so I do a little bit of climate activism and advocacy, and read as much as I can about the issue, and I've taught classes, taken classes on the topic before. And so there are other directions people are taking that I think are maybe not as useful as it would seem. So for example, this notion that we might develop better catalysts to turn carbon dioxide into plastics. That might make a little bit of a difference. But if you actually look at the numbers for how much plastic consumption there is in the world, and how much CO2 would have to be captured to actually solve the climate problem, there's a huge mismatch. You'd never be able to produce enough plastic to actually make a dent in the climate problem.
Yeah.
So that's not really a comment about quantum computation. It's just, you need to make sure that you're looking at really the overall global numbers before you decide what kind of technology you're going to work on.
Yeah, but I think this is a great point. And something that I'm definitely guilty of, which is not doing, making claims that intuitively make sense, right? But not doing quantitative analysis to actually make sure that the impact is of the order of 10% and not 0.001%.
Yeah, that's actually, what you just described is my main source of irritation in life these days is seeing when people draw, again, I'm just speaking for myself, right?
Sure.
When people kind of make claims about how plastics is a big climate problem, to take that as an example, because I hear it so often. I'll have a friend find out that I, in my free time, I do some climate change work, and often I'll get a well-meaning comment about how they recycle a lot, or they'll ask me how much I recycle. And the thing is, plastics are, the numbers are somewhere between like 1.8 to 4% of global emissions. Mm-hmm. And it depends how you account for things. And I think the higher number is a bit unfair because you would have to have substitutes and stuff. It wouldn't really be 4% if you got rid of plastics. But, the primary source of emissions is burning fossil fuels, not producing things from them. And so if you're really going to prioritize things, then the things to prioritize are essentially the electricity sector and transportation. So in America, very, very roughly speaking, actually a few years ago, transportation overtook electricity as the biggest emitter in America.
Oh.
And they're both somewhere like 40% each.
I see.
Right. So that's what should be focused on, in my view.
Sure.
Right.
So, but this is from the perspective of climate change, but isn't plastic also like a big issue for like other environmental reasons?
Oh, absolutely. It's an enormous issue.
Okay.
Yeah. And that's what I usually tell people is it's an enormous issue. It just isn't that relevant to climate change. Yeah.
Sure.
There's lots of issues that I care about a lot, defense of democracy, all sorts of human rights issues, but it just doesn't happen to fall in the category of climate change.
Sure. Yeah, I think this that makes a little sense. And actually, I'm curious about the kind of activism that you are doing. Could you tell a little bit about it?
Sure, yeah. So I spend a little bit of my free time with an organization called 350 Silicon Valley. So the group does all sorts of things, really. Kind of runs the gamut for different types of climate activism. We have teams that try to look at legislation, new laws that would affect climate change, like new building codes, like, laws that would increase the number of sales of electric vehicles, that kind of thing. We have teams that look at the city level. We have teams that kind of try to influence California government in Sacramento. And then we have a team that's focused on federal legislation. And then we also do educational events, things like that. But I think one of the more impactful things is these meetings that we have with politicians, trying to convince them to support certain laws. And there's been a lot of progress recently. So, our organization can't take credit for a lot of these, but, we're part of coalitions that support things like banning natural gas in new buildings in Silicon Valley. Mm-hmm. So this was a set of city laws that really took off like wildfire at the end of 2019, I think. Basically, a lot of cities have banned natural gas in new buildings, right? You probably know that there's issues with methane leaks, right? Methane is at least tens of times more powerful a greenhouse gas than CO2. And of course, when you burn it, it still emits CO2. So there's been a big movement to remove methane use from buildings. At the end of 2019, the California legislature passed a law saying that California would have 100% clean electricity by the year 2045, I think. That was a bill called SB 100. And so it's rewarding to see that a lot of this work that is done by lots of organizations, not just ours, actually leads to really concrete results and can make a difference. And
so I think there are a lot of people that would like to make a difference, and they don't know how to do that. They recycle, they ride on a bike to work and like things like this. But, it's worth doing, but at the same time, it's not really how one person can make a huge difference. So I was wondering whether you have any advice or ideas for people, and given the audience, I think especially researchers, engineers, people working in science, is there anything they could do to actually make a difference here?
Yeah, great question. I guess my own view is that you kind of need to pull the levers that are the biggest, right? In any situation. It's pretty late in the game for climate change, to be honest. I heard a quote. It's something like, if we all changed our light bulbs 20 years ago and started, eating more vegan, then it might have made a difference. But at this point, it's kind of too late for individual actions. And so, things like pressuring politicians. By the way, you'd be surprised at how amenable they are to having meetings with you.
Oh.
And you'd be surprised at how few emails they get from people. I've heard from people who are, aides inside governments. I've seen things that they've written. And they say that, just like an extra 20 or 30 emails on a given topic can easily change their votes.
Wow.
Especially if it's someone like a city council member who never hears from anybody, and then all of a sudden they get 10 emails about how, they really want you to add more charging stations around City Hall. They do listen, right? And even at the state level, that seems to be the case too. But back to your question. I mean, it's a big lever point in my opinion that we should go with. I know there's going to be disagreement with that. A lot of people think that we should focus on flying less and biking more and that kind of thing. It's a little bit hard to see how that would move us fast enough. But yeah, you said a lot of people who are listening are engineers and that sort of thing. I mean, hopefully the number of clean energy jobs, including jobs for engineers and the high level work, are going to increase. If I wasn't working in quantum computation, I would love to be, pushing the technology forward. And there's lots of opportunities there. Maybe in a few years, there's opportunity for quantum computation people to make a dent.
Yeah, I hope so. And my point on kind of flying less and eating vegan is, well, I think it's still worth doing, but
yes,
we shouldn't disillusion ourselves that this will make a biggest difference. And so one of regarding this activism, because it seems like really high leverage, sending emails isn't that hard. I'm curious, how much time does it take you? Is it for you full-time job to be involved in this type of initiatives, or is it a couple of evenings a week? I feel that there are a lot of things that people could do. They just think it will take so much time that they don't even try getting involved. So I'm curious, how it works for you.
Yeah, those are great questions, and I agree. It is actually really, it can feel tough to know how to get involved if you care about an issue. To answer your first questions, I mean, a few hours a week, standard hobby levels. It doesn't cut into my real job very much at all. There's meetings where we plan things. I run a session online where we write these emails to politicians, right? And it's kind of a good way to get people's feet wet, get them into the organization. Mm-hmm. I haven't thought too much about this actually.
But it doesn't sound like, a second job or something like this.
But one really important point that isn't necessarily obvious that I've realized is in the volunteer world, people are really forgiving, if you kind of have to back out or kind of if you overcommit at first and then decide it's too much. Everyone, all the reasonable people, which is the majority of them, everyone understands that you might join an organization and then, like I said, maybe you've overcommitted a little bit and then you can step back. I mean, there's not the same kind of guilt that you have to feel that you might feel if you commit to a project at work, right? If you have to back out. And so people shouldn't be afraid of kind of getting involved, seeing what they like. Maybe they start by helping organize educational events in some organization, and then they decide I don't actually enjoy that so much. Maybe I'll move on to doing something a little bit more political. Mm-hmm. If you move around, everyone knows that no one's getting paid, right? Yeah. You should be trying to have fun. You should be trying to pick something that you enjoy. I know there's a mission, right? In the case of climate change or maybe some human rights organization, there is some goal. But at the end of the day, it's still your free time, and everyone's going to respect that. So I guess if I could encapsulate this in some advice for people who want to be an activist, I would say just shop around to different organizations and shop around in different roles, and eventually you'll find something that you both enjoy and find fulfilling because it fulfills the mission. Do you have much history in advocacy and stuff?
No, not really. I would say with the work I do at the Quantum Open Source Foundation. So, for example, yes. I'm running this mentorship program. So, it's also not taking that much time. At least my time. It's probably a couple of hours per week, and they're more intense periods and some when nothing's really happening. But yeah, I focused more on quantum computing, education, and growing community and this kind of stuff. So the only thing connected to climate change is the Q for climate for me. Okay, so going back to maybe not climate change, but one last question I would have for you regarding important issues before we dive deeper into the research is ethical development of technology, of quantum computing in particular. So it's recently that there have been some initiatives around this topic. And I'm curious, do you have any thoughts how important it is, and what we could do either as like individual people in companies or as community do to like make sure that this technology will be used more for good than for, I don't want to say for bad, but we'll make sure that the technology is not used only for bringing profit to stakeholders, but rather actually focusing on changing something in the world for better. Any thoughts on that?
Right. Yeah, that's an awesome question. I don't have any special insight into that, I would say, but I have kind of noticed that there's quite a few programs that have popped up in machine learning, right? Because people are concerned about the ethics of machine learning. Everything from facial recognition to, I guess a lot of the main stuff is surveillance issues, but maybe also things like weapons design, right? People are concerned about all these things. And I think I don't go to the machine learning conferences, but as far as I know, a lot of those conferences now have speaker programs and even accept papers specifically on the ethics of ML. I guess it just seems like the quantum world, if this is a concern, should build up those kinds of official programs,
sure,
so that people can be taken seriously and gain a little bit of prestige when they decide to focus on those problems instead of just doing math all day, right? Yeah. What do you think?
Makes sense.
Sounds like it's a topic you've thought about.
Yeah, I think one thing that people could do is just civilian courage, to just see if something is going wrong at your company or your organization, then just speak up and ask questions. So I recently read the book
Absolutely.
Flash Boys by Michael Lewis. It's about the high frequency traders on Wall Street in 2009. And the thing is that a lot of those people who are software engineers and writing basically software for exploiting the market had little awareness of the consequences of their actions. And they were just, solving extremely difficult technical problems and just trying to make algorithms run as fast as possible. And they were not really thinking about the consequences and the fact that basically people are getting ripped off because some bank has capability to exploit individual traders or things like this. And I don't know, I feel like just having people in the field who think about these issues might already help, because in certain situations it might tip the needle and make the whole organization make better decision. I guess in most cases it doesn't matter, but there are certain cases where it probably does. And just the building culture of actually being mindful about the consequences of your action.
No, I agree with all that. Do you think it's encouraging that a lot of all of the big tech companies seem to take dissent relatively seriously?
Yeah, definitely.
Internally?
Yeah, definitely. I mean, I've seen with just talking to people at Zapata or at other organizations, it seems like people are actually thinking about these kind of topics. And most of the people in quantum computing I talked about, they take these kind of considerations. They have it in mind. So it's reassuring, but at the same time, we'll see how it goes.
Yeah. Hey, can I ask, what are the main ethical issues that you have in mind for quantum? Is it the fact that Shor's algorithm makes it so I can do any decryption of existing emails?
So I haven't thought about it very carefully, and for me, it's more about things we don't know, and that we should probably just think about it. But one thing I'm slightly worried about is that the access to the hardware might be limited, in the sense that if you have academic users that are doing research about, using quantum computing to solve climate change, to be very vague, there's no immediate value in that, and the access to the hardware might be very expensive. So it might turn out that even though they could push their research a lot by using quantum hardware, it might be just too expensive, or they might be not able to get access because the access is very scarce. While at the same time, some people will be using it for just making money. And it's not that like I think there's something inherently wrong with making money, but I guess if the world could be a better place if the ratio is not 99.9% to whatever stressed, but rather like maybe 90 to 10 or something like this. Absolutely no answers. Maybe I'm totally wrong here. Maybe kind of, this perspective is in some way inherently biased. But yeah, just like thinking about these issues, it's like one thing that I thought about. Okay, so let's now switch gears a little bit and focus more on your research. Well, as I already said, like I come from software engineering background, and I have little knowledge about what your main focus is, which is quantum chemical physics, quantum chemistry, materials, and this stuff. So, could you give a quick overview of the fields you're interested in, and basically talk a little bit how what are some subfields, which are the ones that you focus on, and also not necessarily only about in the realm of quantum computing, but also give some context how it looks like in regular kind of classical chemistry, let's say.
So it's theoretical chemistry, computational materials. These fields are incredibly broad. Mm-hmm. I mean, think of any substance around you, in any context, regardless of where you are in the world, whether you're out in nature or in your room looking at different objects. It's likely that pretty much everything that you're looking at has been, someone has attempted to simulate it and study it in the context of theoretical materials or theoretical chemistry, right? So it really is like any substance that you can see. And most of the time, those calculations are pretty approximate, So you might be able to not exactly predict the rate of some chemical reaction. You might not be able to exactly predict the energy of it. But if you can simulate it, oftentimes you might be able to look at what the simulation is doing and kind of qualitatively have a stronger understanding of what's actually happening. Maybe you don't know what the mechanism is of what's happening in the reaction just by running the experiment. But, if you actually do the simulation on your computer, then you can maybe see that like a ring, you have like an organic ring opening when some particular molecule comes in to start the reaction. And that's really important to learn that kind of thing. So there is a subset of problems that can be simulated very exactly using classical computers. Mm-hmm. It might require a supercomputer, but there is a set of problems. Either they're small enough or simple enough, or the property is simple enough, I guess,
sure,
that you can predict the result. Yeah.
Can you give an example of a problem which is like not small, but just like simple enough or has like enough symmetries that even though it's like something, I don't know, really big molecule or something else, that it's actually solvable?
Right. So, I mean, if you're going beyond the sort of really obvious things that are solvable, like very small molecules.
Hydrogen.
Right, exactly. One good example is, and there's been huge progress just in the past couple of decades, is the simulation of water. Mm-hmm. Right. So a single water molecule you can accurately simulate using a algorithm called CCSDT, a coupled cluster.
Yeah.
But when you have multiple water molecules together, like a cluster of them, 2 or 3 or 4 or 10, and maybe you have some substance inside of it, right? It's really important to study that problem because it relates to so much in life, right? All of biology takes place in water. All of atmospheric chemistry involves, aerosols and water clusters and stuff. It's insanely important to humankind, right? And so there's been huge progress in highly accurate simulations of that. So the algorithmic development has been really intense. And I don't know how much I should get into that, but it's partly on my mind because my undergraduate advisor was Francesco Passani at UCSD, and he's been, really groundbreaking in this field. Just 10 years ago or so, you wouldn't have been able to predict what the absorption spectrum is in water. You wouldn't have been able to predict certain things, maybe like diffusion constants. You wouldn't have been able to even study how water freezes. Things that you might think are simple that might have been simulatable in the 60s. Because this is a big quantum problem, it's really difficult to do. But based on essentially like a pipeline of methods where you kind of start with coupled cluster for which you can actually simulate up to, I don't know, something like 20 water atoms or 20 water molecules. you can kind of take the results from that and move kind of to a next step and do some sophisticated statistical mechanics and move on to eventually getting the result that you want. I think that's probably a decent example where I think even 10 years ago we didn't think that it would be simulatable, but now using classical computers you can get accurate results for certain properties of water. And that's actually important that we bring that up because, there are problems that we think are intractable that will require a quantum computer, but there's always going to be this competition between classical and quantum computation, especially early on, right?
Sure. And is it really even a good idea to draw distinction between material science and quantum chemistry and chemical physics and so on? Or right now these fields are very intertwined and it's not always very easy to say where exactly you are and whether the problem is from this domain or other domain?
I think most people or most researchers in these fields would say that computational chemistry and computational materials are pretty related.
Okay.
And it's hard to define these terms, right? It's totally arbitrary.
Yeah.
In principle, you could say that all of chemistry is a subset of material science, or you could say that all of materials is a subset of chemistry, right?
Yeah.
But there are some kind of subtle differences. There's a ton of overlap, but there's some subtle differences. Like, for example, periodic materials are more commonly studied in material science departments, so like crystalline materials. But there are quite a few theoretical chemists who study them too. And there is a misconception with some people maybe that, the materials only refers to kind of periodic crystalline materials. But, in material science departments, they also study things like polymers, like, things like that. So I would say there's not a very strong distinction between the two.
Okay.
So others might disagree.
And is there anything that makes you, except for the things that you are working on that we'll get to in a moment, but is there anything else that makes you particularly excited in this field, either on a classical computing or quantum computing side?
So, do you mind if I give kind of a more general pitch for the field?
Yeah, sure.
So, the goal of computational chemistry is to be able to simulate anything before you get into the laboratory. That's what would be incredible. At the moment, like I said, you get kind of qualitative results for a lot of things. Maybe some things you can get quantitative results for. But imagine being able to simulate like a new battery material and know ahead of time, before you spend any money in the laboratory, before you buy any labor, knowing ahead of time that it would work the way that you predict it to. Same with like a new solar panel or a drug, for example. Right? This is kind of the dream of the field. Right? Decades and decades we've been building up all these methods. It's the ability to be able to predict anything ahead of time. So those are actually some good examples. It's really exciting to me that you might be able to, have accurate predictions before you run the experiment of like a new battery material, for example, or a new solar material or a new drug. Drug discovery is a good example, actually. What they do, I described this earlier, they screen, maybe 1 million molecules, and then they take what seem to be the top 100, and then maybe only a few of those work. With a quantum computer, it would be difficult. It's probably not the first application that would show up, but you'd be able to essentially have high confidence that your result is accurate. And it's incredibly exciting. Effectively, you'd be putting a lot of people out of work, right?
I mean, I'm sure those people will find other things to do.
Of course.
With this kind of expertise, I guess.
They'll move on to some other section of the pipeline. But
Yeah.
But I should also say, probably your viewers are familiar with something called chemical space, right? So one thing that quantum computation won't be able to solve is actually searching through molecules. So there's some statistic that the number of organic molecules of 20 atoms or less, I'm saying the approximate version of this,
sure.
But the number of organic small molecules that in principle could exist is larger than the number of atoms in the universe, right? It's like 10 to the power of 80 or something.
Yeah.
So you'd never be able to search this whole space. And that's one problem that quantum computation probably can't solve, right? It can solve the problem of an individual material, but not of searching this massive space. So once we have a quantum computer, there's still all these other interesting, intractable issues that come up, right?
Oh, sure. And by the way, I also recently seen some research from Alan's group about using generative models, like machine learning generative models to simulate molecules. And that also looked pretty exciting.
Yeah, I'm excited about that stuff too. I try to follow those papers.
And like another problem that's very important in this field is the problem of electronic structure. So basically, as I understand it, it boils down to finding the wave function and associated energies of a molecule, or like quantum system in general, so that then we can describe it better and understand how it works. But the problem that you are mostly focused on is vibrational structure. So I wanted to ask you, what's the difference between these two, and why do you find... You touched on this at the beginning, but like, why do you find the vibrational spectrum topic so interesting?
Yeah, so part of the reason is that I came to the field late, and all the good topics in electronic structure had kind of been captured already.
I see.
But what you were saying was correct. I mean, generally for electronic structure, I'm sure everyone knows a molecule or material is made of nuclei and electrons,
yes.
right? And so for these calculations, you clamp the nuclei in place, and then you just solve essentially for the electronic wave function as you described. And then you move the nuclei, you do it again, you move the nuclei, you do it again, and then you get the energy as a function of the positions of the nuclei, right? This is called the Born-Oppenheimer approximation.
Yeah.
But there are all sorts of cases where the step after that, where you actually look at the dynamics, while these atoms are moving along this surface, this energy surface, there's all sorts of cases where that's actually intractable computationally, classically. And so, the insight we had on one of our papers was that, you can kind of categorize all these simulations first in terms of whether the electronic problem is tractable or intractable, and then, on the other dimension, whether the vibrational problem is tractable or intractable. And it's interesting to focus on those cases where you can use some really sophisticated method like coupled cluster to solve that energy potential, but where solving the quantum vibrations that come out of that energy potential are not going to be easy to solve. And so that's kind of what we're focusing on. I should take a step back and say it completely makes sense that the first topic that one would care about is electronic structure. Uh-huh. There's more applications for which that's the bottleneck. But a method like coupled cluster is really good for main group elements, essentially. Elements that don't include the transition metals.
Yep. And
in those cases, you can get accurate results for something like more than 1,000 orbitals.
Whoa.
So, right. So, there's at least one paper that looks at, I think it's a few thousand orbitals for a very large water cluster, right? And so coupled cluster actually does surprisingly well for those types of molecules. It doesn't work very well for transition metals. But the point is that in those cases where you have some kind of like floppy molecule, you have things that kind of deviate from harmonicity, is essentially the way to look at it. In those cases, you might be able to use a quantum computer. And the other major point there is that we think, we haven't proved this directly, but we have a lot of circumstantial evidence that a vibrational problem might be the first problem that's solved on a quantum computer rather than an electronic structure problem. And the way we came to that kind of hypothesis or conjecture was by, looking at the structure of the Hamiltonian that you would expect from the vibrational problem versus the electronic structure problem. One thing we haven't pointed out is, at least for near-term methods, electronic structure probably scale is something like n to the fourth.
Okay.
Maybe slightly better. There's a lot of amazing work in the more medium-term or long-term methods, especially some of these papers with Fumoko that we mentioned, where they can get much better scaling, n cubed or n squared, or maybe even n polylog n. But for, if you only have less than 100 qubits or maybe a couple hundred qubits, it looks like those better scaling methods probably won't work. And so for the near term, you probably need one of these more like n to the fourth type methods.
Sure.
And for these vibrational problems, there's quite a few classes where you have an n squared scaling. And so it seems like for near-term applications, there's a chance that vibrational problems might be solved first, at least for that subclass of vibrational problems that can be described with n squared terms.
Sure. And so vibrational, correct me if I'm wrong, but what I get is that vibrational problems are about how the parts of the molecule are moving in relation to one to another, right? How do they kind of oscillate, vibrate, and how this affects the spectrum and like the behavior of the molecule, in kind of generally speaking, right?
Right. Spectrum is one thing that you can look at. One important thing that we look at quite a bit. What happens when you shine light at something, or what light does it emit, right? And that's important for all sorts of applications. Even things like analyzing combustion reactions, let's say. But it's not only that. So, often if you're just interested in like the energy of a reaction, so this won't be true for all reactions, but for some reactions you have to consider the energy contributions of the vibrations just to understand what the total energy of the final product is, right?
Okay,
and to understand things like rates, right?
Okay. So I guess the thing is that in case of some molecules, this vibrational energy is relatively big compared to the like other energies that there are. In some other, they're this like negligible. So in this case, you kind of don't care about it.
Yeah, not negligible, but just very easy to calculate.
Okay. That's the point.
Right. And so yeah.
What are the characteristics of the molecules where this is an important problem versus those where it's still important but it's like trivial to calculate?
Yeah, so the main metric really is how harmonic it is. So basically, I described this energy surface before. You move the atoms and it goes along this quote unquote surface, energy surface. Basically, in molecules that are more rigid, which really is most molecules that you probably are familiar with, like, whatever, water, caffeine, all these diagrams you see maybe here and there. Most of those are relatively rigid. And in those cases, basically, the atoms move, conceptually speaking, along parabolas.
Okay.
Or paraboloids, right? Physicists should be familiar with normal modes. You essentially calculate the normal modes of the molecule, and then it moves in these harmonic directions, and basically that's easy to calculate because there's no mixing between the modes. So everything's kind of what physicists call a product state, right? But then if you have something that's floppier, that means that even if the molecules move just a little bit, they kind of are outside this parabola regime. They're outside the harmonic regime. And because of that, you all of a sudden have all these couplings between the different vibrational directions. Okay. And that's what leads to this really complex, completely arbitrary Hamiltonian that you have to solve. That's the main metric to think of it as. And that also, I mentioned combustion reactions. I mean, a lot of intermediates in reactions are kind of floppy, for lack of a better word. And so, to calculate the energies of those intermediates in certain types of reactions, of which there might be quite a few, you can't just consider the harmonic approximation.
Okay, I get it. Okay, so when it comes to translating this problem to a quantum computer, I guess one thing that you said is that Hamiltonians, like certain Hamiltonians, are just like relatively easy versus relatively hard to solve. So can you take basically the same methods, or let's be specific. Can you take like VQE and feed Hamiltonian for the electronic structure problem and like solve it with VQE, and then later take the Hamiltonian for the vibrational problem, and because that's basically the same quantum mechanical Hamiltonian, like just like put it there and solve it? Or are there some tricks or some specific things that you need to care about when it comes to solving this type of problems this way? Yeah,
so you're saying sort of can you use VQE for that first step of the electronic structure and then feed that into VQE for the vibrational degrees of freedom?
Like use the same VQE basically, just like swap the Hamiltonians.
Yes. So yeah, and then the main difference there is that the mapping that you use is different. It's actually it's essentially much simpler, right? So there's Jordan-Wigner and Brodby-Kitaev and a couple other mappings that you would use for electronic structure. But you don't have that fermionic commutation relations for the vibrations, right? It's bosonic commutation. And so you end up having other considerations. You have to decide how to like truncate your bosonic space.
Okay.
But yeah, essentially you can use the same VQE methods. One other thing in line with what you're saying is, there are times where you have to kind of combine both degrees of freedom, right? This separation between vibrational and electronic degrees of freedom is called the Born-Oppenheimer approximation. But there's something called conical intersections, where essentially you're, it's if you're at nuclear positions that make it so that two different electronic energy surfaces are close to each other. People can Google conical intersection to look it up, but in those cases you can't just separate out the problems. You have to use more sophisticated methods, or just simulate all degrees of freedom together.
Sure, I see. And just like one follow-up question regarding this VQE example is that for electronic structure we usually care about the ground state, but it seems to me that for the vibrational problems we actually might care more about some excited states, because when that's maybe silly, but when I think vibration, it's for me it's like sounds like excited states. Things are moving, there's a lot of energy, and it's not like ground state. So is this also something that's actually matter and like informs some decisions when it comes to like designing algorithms for this type of problems?
Right. Yeah. So there is still a ground vibrational state, and in quantum mechanics, nothing is ever standing still, right? So even the ground vibrational state is moving in principle. But yeah, what you said about excited states is very important. So in electronic structure, oftentimes you do care about excited states. You might care about the molecule or material absorbing light, in which case you care about the excited states. But the issue with but normally you only care about a few of those states. You almost never care about the 10th excited electronic state, for example, right? But in vibrational structure, because these levels are much more closely spaced, you care about way more excited states. And it's not uncommon to have a situation where you care only about the high-lying states. So an example of that is molecules. I brought up the example of astrochemistry earlier. In molecules, you might only care about one section of the infrared spectrum. Maybe your telescope can only read one section of the spectrum or something. Maybe it starts at 1,000 wave numbers or something, right? This is the energy of the photon. And that means that you're not interested in calculating everything between 0 and 1,000 wave numbers. So you just want to start at maybe like the 100th excited state.
Sure.
And in that case, we bring this up in one of our papers. In that case, you can't use the method, or you probably wouldn't want to use the kind of standard NISP methods that have been developed for excited states, because all of those are built up kind of like you start with the ground state, then first excited, then second excited. And so that's an interesting area for new research too. Near-term methods for high-lying excited states.
Sure. That's interesting. And like nothing that I really heard about earlier. Like most of the things that I've heard about were ground states and like maybe first, maybe second excited, but not like 100th excited state. So
right.
What are some other applications? You mentioned astrophysics, but when it comes to applications, where this type of problems seem to be relevant?
Yeah, so astrophysics, I think, or astrochemistry is a really cool one. I think it's cool because I didn't really know about it before I started this project. Oh. And it looked like this was a good application. Combustion reactions I mentioned already. So, if you burn something, even very simple molecule, a fuel, maybe you have some biofuel, if we stick with the climate change theme. Sure. Then, you have lots and lots of intermediates. There's been researchers who have tried to like map out what all these different molecules in between are, right? And it's this incredibly messy situation. To analyze all those intermediates, in principle, you might need to be able to have a quantum computer to simulate the ground vibrational energy of each of those intermediates. Right? No one's done that so far. I don't think, because it's there's so much to study in that problem area. But some other applications are atmospheric chemistry. So understanding things like aerosols, how clouds form, how a pollutant or how a non-polluting molecule might affect those types of things, has to take the vibrational degrees of freedom into account. That's not spectroscopy. That's just being able to accurately simulate the motion, right, in a quantum way. And then there's something called analytical chemistry. It's a branch of chemistry where you try to identify what you're seeing, or you try to take very precise measurements. So that's essentially what the astrochemistry problem is. You're trying to identify what you're seeing, right? And then there's all sorts of properties of materials that are based on vibrations, things like heat capacity have to take vibrational degrees of freedom into account. Things Makes like sense. Coefficient of conductivity, thermal conductivity, that kind of thing. Mm-hmm. Yeah, so there's all sorts of things where vibrational degrees of freedom are actually, the hard part.
Yeah. That sounds pretty interesting. And one of the things that kind of you briefly mentioned before was the encoding. So what you mentioned was that we have Bravik-Kitaev or Jordan-Wigner ways of like taking basically a quantum mechanical system and then like map it to the qubits. And for me, the problem of encodings first came from very different place. So when I was working on using QAOA to solve traveling salesman or vehicle routing problem, mm-hmm. I started to think, what are different ways of take basically the same problem and just encode it in a bunch of zeros and ones. And it turned out that, well, A, it's highly untrivial, but B, there is a lot of trade-offs here. So, for example, that one encoding gives you lower number of qubits, but then much bigger circuit depth, while another maybe is pretty compact, but it's so hard to actually think about this problem, like in human terms, that it's very hard to like develop anything. While yet another, gives you relatively low qubit count, relatively low circuit depth, but the energy landscape of the optimization function you're trying to optimize gets just so hard that it's just better to use more qubits and solve a simpler problem. And
so you found that the optimization is much harder if you have a more kind of compact encoding.
Yeah. It happened. So
interesting.
The thing was, that wasn't like very rigorous analysis, but the problem was that when I started adding constraints to the problem, so basically combinatorial optimization problems are usually, if not always, kind of integer problems, right? So the problem is that there might be certain solutions which don't have physical sense, right? So, for example, in traveling salesman, you cannot be like in 5 cities at the same time. So you need to add constraints to your problem. But when you're trying constraints, they are just like making it much harder for the optimization landscape, because sometimes you just add certain costs associated with breaking this constraint. So then you have like a lot of arbitrary constants in your Hamiltonian, and it might get very messy very quickly. And I've read your paper about the encodings, and could you like quickly describe what the paper was about and what were the main takeaways?
Yeah, I think you almost covered all of these issues. So we did look at the the different trade-offs for the different encodings, and we introduced a couple of new encodings also. But like you said, roughly speaking, some of these encodings might require more qubits, but those would require less depth, right? And then the other encodings might require more depth but fewer qubits, right? And so depending on what hardware you have, you can kind of tailor these encodings to the specific hardware. There's been some papers that have suggested that, this one-hot encoding, or it's also called the direct mapping or the unary mapping, we call it the unary, is the only way to go for near-term applications. I don't think there's enough evidence to suggest that that's true. One of the reasons I don't think there's enough evidence for that is the reason you just gave. You essentially leave the manifold much more easily if you're using the unary or one-hot encoding.
Yes.
Right. There's all sorts of, even a small error makes it so that you have an issue where you're like, in 5 cities at once, as you suggested.
Yeah.
Or a situation where you're, where you measure and you're in 3 vibrational modes at the same time when that's not allowed. And if you are taking up the entire Hilbert space with your encoding, then you don't have that issue. You'll still have systematic errors, but in principle, that might end up being fine in some situations, because then your VQ optimization just cancels out the systematic error in principle, right?
Yes.
The other thing we introduced in that paper was the gray code in this context. So that's a really old concept from computer science, I guess. And it's another binary encoding, right? It's a little bit different from the base 2 encoding. Basically, each integer has a different bit string than you would expect. Computer scientists should be really familiar with this. But basically, between adjacent integers, you're only flipping one bit, right?
Yes.
So because of that, and because a lot of matrices that you have in condensed matter physics and in chemistry are tridiagonal, essentially a lot of these matrices, you only care about nearest neighbor integer interactions anyway. The raising and lowering operators are one example of that. Because of that, the gray code ends up being kind of useful. When you do early analytical studies, it looks like the gray code is going to just be amazing. The actual speedups are, between 0 and 30% instead of the large speedups that we thought. So that's like a constant factor speedup, right? Might be helpful in a lot of VQE situations.
Sure.
To use the gray code instead. So still a modest speedup if you're trying to squeeze as much as possible out of there.
By the way, I think that I haven't seen too much use of gray code in like quantum computing encodings problem before. Maybe that's like I just missed the papers. But when I read this, it was like, wow, it just makes sense to use gray encoding, because it for the reason that you just described, it's like maps so well and solves a couple of issues that I encountered.
Right.
So actually, have you seen a lot of other research where people used gray encoding, or not really?
Not yet. The paper came out only a year ago, but I've seen a few things where they use gray code in other contexts. Like, I think there was there was a paper from a Hungarian group. They presented something at the IEEE Quantum Conference.
Yeah.
Whenever that was last year. And I think they were the ones that used the gray code kind of in tandem with quantum phase estimation to do something slightly unusual. So that's a totally different use of the gray code. Mm-hmm. But in this context, I see mainly a few papers continuing to insist that the unary encoding is the only way to go, which, like I said, I disagree with.
Sure.
So that's kind of been that's been one thing I'm noticing, but that's nice to see that you're using it and I'm continuing to use it. So
I mean, not using it. It's just like not. I hope I will use it one day. But
sure.
Actually, another encoding you covered is this block binary or block unary encoding, and this is, as I understand it, it's like a trade-off between using unary and binary. And I also noticed that in one of the papers by Adam Gloss, he had a couple of papers about encoding as well. And could you tell us a little bit more about this, and what are the trade-offs, and why do you think it's an interesting concept?
Right. So as you said, the whole reason for introducing that block unary encoding was to try to kind of tune, like have tunability between the number of qubits and the circuit depth that you have, right? Now, the block unary ended up being kind of disappointing, but it looks like there might be a few very limiting cases where it would be the optimal choice. But basically, this topic of tuning between those two degrees of freedom is a really interesting topic, because it means that you might be able to squeeze as much as possible out of whatever hardware you happen to have, right? But yeah, if you're asking specifically about that encoding, I think it probably won't be used very much, to be honest. But that general topic of how you might interpolate between the unary and the completely compact binary codes is a really interesting open topic, I think. Mm-hmm. I think someone who has a much better background in like error correction codes maybe would be able to solve that problem better than we did.
Sure.
That's a cool topic.
Oh yeah, it really is. So another thing that I'm curious about is, what do you think, how the situation will change once we get a lot of qubits? So this is a very important problem in the regime of limited number of qubits. However, if we get into millions or billions on qubits, do you think that, and probably also like much lower error rates, like error fault tolerant computers, do you think that like some of these encodings is actually superior in that regime to the others, or still not necessarily?
It seems just, the first impression is that once you have much more, I guess, memory to play with, that those unary ones would be better. One thing we haven't mentioned yet is there's also this issue of swapping all the information around, right? We presented a paper at IEEE Quantum that was kind of a really simple little paper on looking at that question, like how much scheduling would have to be done for the different encodings. But assuming that the scheduling doesn't really change this problem we were talking about, or change the basic trend we were talking about, it seems like the more memory you have, that the more likely it is that you'd want to use unary.
Okay.
And that's kind of analogous to situations in traditional computer science where you use just a ton of cache even though you don't need to because it speeds up the problem in some way, right?
Sure. Okay. But and yet another perspective on that is something I encountered when I tried to use unary encoding versus binary encoding. And it turned out that unary encoding was just so much simpler to kind of think about. And if you have, like in traveling salesman, like 5 cities, then unary encoding is basically only one in one position and then zeros. But then if you try to convert it into binary encoding, then there's like no inherent structure because you're just like representing integers as zeros and ones, and it makes it very hard to kind of think and like design your algorithm, or at least your mapping. So I was curious, have you also noticed this kind of issues in your work?
Yeah, I'm working on something related to this, and I completely agree that it's much easier to think in unary because the labeling of the qubits just corresponds to the labeling in the problem, right? I think there's ways you can kind of like take kind of abstract, kind of move up one level in the abstraction, so that you're thinking about the problem more in the terms of the original problem, and then kind of just do the mapping in the last step. I'm not sure I described that very well, but I should just say I agree that's an annoying problem. And I think automated tools for that are necessary. I don't think there's any point in trying to make some big conceptual leaps and trying to, have a different conceptual understanding for these mappings for each different encoding type you might use.
Sure.
Automated tools are the solution.
Yeah, I couldn't agree more with that. Okay, and now I wanted to segue into another paper that you authored, which is about Q-dits, and it also like ties in nicely into thinking about the problem, because, well, if you are forced to think about the problem in terms of zeros and ones, it doesn't work very well, especially for combinatorial optimization problems, as like traveling salesman, for example, where it's much easier to represent city by like integer ID rather than a bunch of zeros and ones. And I was wondering whether actually Q-dits could be used as this like another layer of abstraction. Do you think that's like possible or reasonable way to approach it?
Sorry, I don't totally understand the question. You mean in terms of preparing the problem, or you mean using hardware that has actual Q-dits as a component?
Okay, so that's like two interesting things here. So one is in terms of preparing the hardware. So just like instead of writing brackets with zeros and ones, just write brackets with like arbitrary n, and then takes those n states and map them onto the qubit computer. That's like one way to approach it. But the other way to approach it is to actually run it on the Q-dit quantum computer, which doesn't exist as far as I know. But like, do you think that's a reasonable approach or not really?
Yeah, I mean, if all you have is a digital computer, then that seems to be what you have to do.
Yeah.
And the paper that you're referring to is really just kind of an addendum to the original paper that you brought up. So the IEEE paper is kind of an addendum to the NPJ paper, NPJ-QI paper. Yeah, so essentially you would use the methods in the paper that we just discussed and other papers that others have written to do that mapping. And it's exactly the same considerations that you would have with the bosonic or vibrational or physics case, and just doing the same mapping for combinatorial problems, right? On the question of using Q-dits in hardware, that's an interesting topic. I don't want to comment too much on hardware, but I'll point out that for some of these vibrational problems, specifically a problem called the vibronic problem, there was a paper out of Yale and some other places maybe that was published in PRX that used, for the vibrational levels in the molecule, used some kind of resonator. I'm not an expert on hardware, but used some kind of resonator to map that problem into Q-dits.
Okay.
So there's already been at least one demonstration of that in the context of the problems we've been talking about. And, there'd be pros and cons with that method, just like any other method.
Sure.
I think error correction is less developed for those methods and might be more difficult in general. But that's interesting for someone to explore. Yeah.
Sure. Okay, and the last question about the research that I have to you is about the way you work on all those novel methods and the novel algorithms. So it's really easy to take existing algorithm and apply it to a certain problem. You have to figure out a lot of things in between, but like conceptually, it's easy. It's doable. But then creating a whole new method and just, designing a whole new way of looking at a problem, well, that's something that's like really hard. So I'm curious whether you have any, like, how do you approach this problem? Do you have, any methodology or any tips or tricks how to do this? Because like I'm personally just like amazed when I talk with some of my colleagues, like, how the hell did they came up with the idea of doing it in this particular way? I'm just like, like out of league, like totally with when talking about it. I can take it, I can apply it, I can use it, I can understand it, but like invent it, like that's not my league. So do you have any thoughts about this?
Yeah, I don't know if I have very original thoughts about it, but I do have thoughts. I think the key is to look for the gaps first. So essentially look for fields that other people have neglected, and that's where you're going to find the most interesting new problems. I mean, I don't remember which famous physicist said this, but my high school physics teacher would always quote one physicist, it might have been Richard Feynman, who said, the key isn't being good at finding the right answers, the key is being able to ask the right questions.
Yeah.
Right. And another random quote, I saw a talk by Peter Nordlander when I was in grad school, and he was pointing out that what you really want to do as a young researcher is find the fields that are just starting or that are on their way up and kind of like try to work on those. And I mean, your question was more about methods development.
Yeah.
But if you're doing that, then you're going to find the areas where people haven't decided which methods to use yet. And those are the areas where you're more likely to be able to make a methods contribution. I mean, one example is this spectroscopy problem. I mean, we realize that in the vibrational problem, because you care about these really high vibrational states, you can't necessarily use any of the excited state methods that were used for electronic structure, right? At least not for NISP algorithms. So that's just one example where, you wouldn't have even thought to come up with a method for. And by the way, we have not come up with a new method for that. I'm just recognizing one area where a person could do that. But you wouldn't have even thought to come up with a method for only calculating the 100th excited state, maybe, if you hadn't looked at those new application areas. And then, the other thing is, I don't know if you're the same, but I do try to always be learning a little bit more math. So every month I work my way through 2 textbook chapters in a math book. That's not much, right? It's manageable.
More than I do.
Well, it ends up giving you more ideas. Like, for some reason, I never took complex analysis in college, even though I was mechanical engineering undergrad. So right now I'm, finally learning all these things about contour integration and stuff that I never learned before.
Well,
and then eventually,
awesome.
it feeds into something, right?
Okay, so I think we are getting to the end. So I have just 2 last questions. So first is, have you read any interesting books recently that you would like to share with the listeners?
Yes, I'd like to hear your answer too, by the way. But
Okay.
I finished War and Peace by Tolstoy during COVID. That was really worth it. There's a lot of stuff in there about how much of a difference a person can really make in their own life. A lot of kind of long philosophical segues that he goes into. But it's pretty cool to read a long book like that, because normally the books that we all read are like shorter than 300 pages, right?
True.
And so it's kind of a cool journey to go through. And I just finished reading The Plague with my dad, which was worth reading during COVID. A lot of interesting insight into how people behave during crises and stuff. By Albert Camus, right?
Yeah. Now that you say, that's like very obvious choice for pandemics that I haven't thought about before.
Yeah, it's short.
Yeah.
What about you?
So I'm reading right now, and we'll keep reading it for some time. The book called Behave, which is by, I don't remember the name, but the last name is Sapolsky, I think. So basically, it's 700 pages long book about neurology of our behavior at our best and our worst. So, it's like covers the topics of aggression, morality, altruism, and things like this from very neurobiological perspective. But the nice thing about this book is that it's pretty. It goes through all the steps and like explains very complex topic. It doesn't like takes any shortcuts. Like digs pretty deep into different things. So I read it very slowly, and I start appreciating how the brain works, and also it's written in a very light language. So it's just like fun to read.
Interesting.
Yeah,
Behave.
Behave. Yeah.
Right.
And I think, I hope I will finish that in the next 2 months or so. It's like, I'm taking it slow.
Yeah. Steady and slow is the way to read.
That's true. Okay, and the last question is, if anyone would like to learn more about you and your work, where they could find you in the internet?
My Google Scholar page, I guess.
Sure.
I have a little blog too, and a Twitter account. So I guess that's my only presence.
Okay.
Yeah.
We'll link to all that in the notes.
And then, of course, there's the Intel Labs page that I would encourage people to look at.
Sure. We'll link to that too.
Just more generally what the company does.
Cool. Yeah, thanks for that. Okay, so thank you very much for this conversation. It was very enjoyable and interesting for me. And I hope it will be same for the listeners. And, well, have a nice day.
Yeah, this was fun. Thanks so much, Michael.
Thank you. If you would like to learn more about Nico's work, you can check out his blog, Google Scholar, or follow him on Twitter. Links in the notes to this episode. If you have any feedback regarding this or previous episode, don't hesitate to let me know. My email in the notes. And if you like it, please subscribe the podcast in your favorite podcast app so you won't miss the next episode. Thank you for listening.